Hello there, and welcome to Science into Sleep. Tonight, we are drifting into the solar system, a single family of worlds born from the same ancient crowd, each one shaped by forces so patient they make centuries feel like seconds. In this journey, we will wander through the formation of our star and the birth of planets. We will visit the silence of distant moons, and we will trace the invisible architecture holding everything in place. By the end, the vastness above may start to feel less like emptiness, more like a familiar room you had simply forgotten. If you enjoy these gentle journeys through science, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Long before any planet existed, there was only a cloud, a vast cold curtain of gas and dust drifting through the Milky Way. It had been there for millions of years. Nothing rushed it. Nothing told it to change. But somewhere inside, a small region grew slightly denser than the rest. Perhaps a nearby star had exploded, sending a ripple through the cloud like a stone tossed into still water. That ripple was enough. Gravity, the most patient force in the universe, began pulling material inward. Slowly at first, then with more confidence. The cloud started to collapse, and as it did, it began to spin. Think of how an ice skater pulls her arms in and spins faster. The same principle applied here, on a scale almost too large to picture. The center grew hotter. The edges flattened into a wide rotating disk. Astronomers call this a protoplanetary disk. It is the nursery where planets are born. At the heart of this disk, temperatures climbed until hydrogen atoms began to fuse. That was the birth of our sun. Not with a dramatic flash, but with a slow, persistent warmth. A glow that would eventually sustain everything we know. Around it, the remaining material continued to orbit. Tiny grains of dust, each one smaller than a grain of sand. They collided. They stuck together. Over time, these clumps became pebbles. Pebbles became boulders. Boulders became the seeds of planets. This process is called accretion. It is remarkably ordinary. Dust sticking to dust. Yet from that simplicity, entire worlds emerged. This entire process took roughly 100 million years. That may sound long in human terms, but for the cosmos it is barely a pause. And during that pause, something remarkable happened. The disk organized itself. Closer to the sun, where heat was fierce, only rock and metal could survive. Further away, where cold ruled, ice could linger. This temperature boundary, sometimes called the frost line, divided the solar system into two broad families. Rocky worlds near the center, gas and ice giants beyond. That boundary still shapes the architecture we see today. We live on one of those rocky worlds. And everything we will explore tonight traces back to that original cloud. Every mountain, every ocean, every ring of Saturn, every comet in the outer dark, all of it came from the same quiet beginning, the same patient collapse, the same ancient dust. The atoms in your body were once part of that cloud. Imagine that for a moment. The iron in your blood and the silicon in the ground beneath you share the same origin. Both drifted together in that primordial fog, billions of years before either became what it is now. The frost line sat roughly where the asteroid belt is today. Inside that line, temperatures were too high for ice to form. Only silicates and metals could condense. That is why Mercury, Venus, Earth and Mars are made of rock. Beyond the line, ice was abundant, and ice provided extra building material. Planets there could grow large enough to capture hydrogen and helium gas from the disk. That is how Jupiter and Saturn became giants. Not because they are fundamentally different, but because they formed in a colder place with more ingredients. The disk itself did not last forever. Within about 10 million years, the sun's radiation and solar wind blew away the remaining gas. What was left behind was a young solar system, still chaotic, still settling. Planets migrated, orbits shifted, collisions were frequent and violent. But over hundreds of millions of years, the system calmed. Orbits became stable. The violence faded into the steady rhythm we observe today. Now we begin to look more closely at what that dust became. And we start, naturally, with the center, the Sun. The Sun holds 99.8% of all the mass in the solar system. Everything else combined, every planet, moon, asteroid and comet, accounts for the remaining fraction. That single fact shapes everything. The Sun does not merely light the solar system, it governs it. Its gravity reaches billions of kilometers outward, like an invisible hand keeping every object in its path. At its core, the Sun fuses roughly 600 million tons of hydrogen into helium every second. The temperature there is about 15 million degrees. Energy born in the core takes thousands of years to reach the surface. It bounces and scatters through dense layers, like a traveller lost in a forest. When it finally emerges, it crosses the distance to Earth in just over 8 minutes. Light you see at sunset left the Sun before you finished your last breath. That connection between stellar fire and your evening sky is direct and continuous. The surface of the Sun is not smooth. It churns with convection cells called granules. Each granule is roughly the size of a large country, rising with hot plasma and sinking as it cools. Sunspots appear where magnetic field lines break through the surface. They look dark only because they are cooler than the surrounding material. Even a sunspot is still thousands of degrees. the Sun is never truly calm. Even when it appears serene from Earth, it is a roiling ocean of magnetized plasma. Now imagine standing on Mercury, the closest planet. You would weigh about a third of what you weigh on Earth. The Sun would appear nearly 3 times larger in the sky. Daytime temperatures climb above 400 degrees, but at night, with no atmosphere to trap the heat, they plunge below -170. Mercury has the widest temperature swing of any planet. It is a world of extremes, sitting on the Sun's doorstep. Mercury also has a peculiar relationship with time. It rotates so slowly that one full day on Mercury, sunrise to sunrise, lasts 176 Earth days. But it orbits the Sun in just 88 Earth days. So a single day on Mercury is actually longer than its year. That quiet fact often surprises people. Mercury is also surprisingly dense. Beneath its thin, cratered surface lies a large iron core. That core takes up about 85% of the planet's radius. Picture a cannonball wrapped in a thin layer of rock. That is Mercury, in essence. Venus comes next. Similar in size and mass to Earth, it was once called our twin, but the resemblance is only skin deep. Venus has an atmosphere roughly 90 times denser than ours. Standing on its surface would feel like being a kilometre beneath the ocean. The air is almost entirely carbon dioxide, and thick clouds of sulfuric acid wrap the planet in a permanent haze. Surface temperatures hover around 460 degrees, hotter than Mercury, even though Venus is farther from the Sun. The reason is a runaway greenhouse effect. Heat enters but cannot escape. Venus also rotates backward. If you could watch the Sun from its surface, it would rise in the west and set in the east. And it spins so slowly that a single Venusian day lasts 243 Earth days, longer than its own year of 225 days. Like Mercury, Venus offers a world where time moves in unfamiliar patterns. Soviet spacecraft landed on Venus in the 1970s and 80s. The Venera missions sent back photographs of a flat, rocky landscape bathed in an eerie orange glow. The cameras survived only minutes before the heat and pressure destroyed them. Those images remain among the most haunting in space exploration. Earth, our home, sits in what astronomers sometimes call the habitable zone. Not too close to the Sun, not too far. Liquid water can exist on the surface. That single condition, liquid water, appears to be the foundation for everything alive. Our atmosphere is a delicate balance. Nitrogen makes up 78%. Oxygen fills 21%. A trace of carbon dioxide, just enough, helps regulate temperature. Remove any of these layers and the planet becomes hostile. Earth also has something no other inner planet possesses: a large moon. Our moon is roughly 1/4 the diameter of Earth, making it unusually large for a satellite. Most scientists believe it formed when a Mars-sized body struck the young Earth, flinging debris into orbit. That debris coalesced into the moon over thousands of years. The moon stabilized Earth's axial tilt. Without it, our seasons would be chaotic. The climate would swing wildly. Life, if it emerged at all, would face a much harder path. The moon also drives the tides. Every coastline on Earth responds to its pull twice each day. The tides may have played a role in the origin of life itself. Shallow tidal pools, repeatedly wetted and dried, could have concentrated organic molecules in ways that encouraged complex chemistry. The moon, then, is not merely a companion in the sky. It may have been a silent partner in the emergence of everything alive. Earth's atmosphere also scatters sunlight in a way that creates our blue sky. From space, the planet appears as a bright blue marble, streaked with white clouds and brown continents. It is the only planet in the solar system where you can stand in the open and breathe without assistance. That simple fact, so easy to take for granted, is the result of billions of years of atmospheric evolution. Mars, the fourth planet, is about half the diameter of Earth. Its surface is cold, dry, and covered in iron oxide dust. That dust gives Mars its famous reddish colour. But Mars was not always so barren. Evidence from orbiting spacecraft shows ancient river valleys and lake beds. Mineral deposits found there only form in the presence of water. Billions of years ago, Mars likely had a thicker atmosphere and flowing rivers. Something changed. The planet lost its global magnetic field. Without that shield, solar winds slowly stripped away the atmosphere. The water evaporated or froze beneath the surface. Mars became the silent desert we see today. Olympus Mons, the tallest volcano in the solar system, rises on Mars. It stands nearly 22 kilometers above the surrounding plains. That is almost 3 times the height of Mount Everest. It is so wide at its base that if you stood on its edge, you could not see the summit. The curvature of Mars would hide it below the horizon. Imagine a mountain so large it bends out of sight. Nearby, the Valles Marineris Canyon system stretches over 4,000 kilometers. It is 10 times longer than the Grand Canyon and nearly 7 times deeper. Mars may be small, but its landscapes dwarf anything on Earth. Between these 4 rocky worlds, there is a fascinating gradient. Mercury has almost no atmosphere. Venus has too much. Earth has just enough. Mars lost most of what it once had. 4 planets, 4 different outcomes, all governed by size, distance, and the presence or absence of a magnetic shield. Each one is a lesson in how small differences in initial conditions lead to vastly different worlds. The inner solar system is a laboratory of possibilities, and we happen to live in the one that worked out. Between Mars and Jupiter lies a broad region filled with rocky fragments. We call it the Asteroid Belt. It sounds dramatic, like a dense field of tumbling boulders. But in reality, the belt is mostly empty space. If you flew through it in a spacecraft, you would likely pass through without coming close to a single object. The total mass of the entire belt is less than 4% of our Moon. Jupiter's gravity stirred this region so thoroughly during the early solar system that a planet never managed to form here. The belt is not a broken world. It is an unfinished one. Most asteroids are irregular in shape. They lack the gravity to pull themselves into spheres. Some look like potatoes. Others resemble dog bones. A few are contact binaries, two objects gently resting against each other, held together by the faintest mutual gravity. The Japanese spacecraft Hayabusa 2 visited an asteroid named Ryugu and collected samples from its surface. When those samples returned to Earth, scientists found amino acids, the building blocks of proteins, along with water-bearing minerals. The asteroid belt is not just rubble. It is a chemical archive of the early solar system. Most asteroids are small. Some are barely the size of a house. Others stretch hundreds of kilometers across. Ceres, the largest, has a diameter of about 940 kilometers. It is so large that it earned the classification of dwarf planet. Ceres has a thin, temporary atmosphere and possibly a layer of ice beneath its surface. The Dawn spacecraft visited Ceres and found bright spots in certain craters. Those bright spots turned out to be deposits of sodium carbonate, a type of salt. They suggested that briny water had once seeped to the surface and evaporated, leaving mineral traces behind. Even in the asteroid belt, water leaves its fingerprints. Some asteroids are rich in metal. Others are mostly carbon. A few contain amino acids, the building blocks of proteins. Scientists have studied meteorites from the asteroid belt and found organic molecules within them. These molecules are not evidence of life, but they show that the chemistry of life is not unique to Earth. The raw ingredients are scattered throughout the solar system, like seeds waiting in different soils. Now we cross a significant boundary. Beyond the asteroid belt, we enter the realm of the giant planets, and the first of them is Jupiter. Jupiter is not just big, it is a category of its own. More than 1,300 Earths could fit inside it. Its mass is 2.5 times greater than all the other planets combined. If Jupiter had been about 80 times more massive, it would have ignited as a star. Instead, it became something in between, a failed star, a triumphant planet. Jupiter has no solid surface. Beneath its colourful cloud bands, the atmosphere grows denser and hotter with depth. At some point, the hydrogen becomes so compressed that it behaves like a liquid metal. This metallic hydrogen generates the most powerful magnetic field of any planet. It extends millions of kilometers into space, creating a vast, invisible bubble called the magnetosphere. If you could see Jupiter's magnetic field, it would appear larger than the Sun from our perspective. The Great Red Spot is a storm on Jupiter that has been raging for at least 350 years. It is so large that Earth could fit inside it with room to spare. Wind speeds at its edges reach over 400 kilometers per hour. Think of it as a hurricane with no coastline to weaken it, no friction to slow it down. It simply continues, fueled by the planet's internal heat and relentless rotation. Recent observations suggest the spot is slowly shrinking, but even now, it remains the largest storm in the known solar system. Jupiter also has a faint ring system. Most people associate rings with Saturn, but Jupiter's rings were discovered in 1979 by the Voyager 1 spacecraft. They are thin, dark, and made mostly of small dust particles knocked off nearby moons by micrometeorite impacts. You would never see them from Earth with an ordinary telescope. They are one of Jupiter's quieter secrets. Jupiter's influence extends far beyond itself. Its gravity acts as both a shield and a slingshot for objects passing through the solar system. Some astronomers believe Jupiter deflects many comets and asteroids that might otherwise strike Earth. Others argue it sometimes redirects objects inward, increasing the risk. Either way, Jupiter is not a passive giant. It shapes the traffic of the entire inner solar system. Its gravity even influenced the final positions of the other planets during the solar system's early chaotic phase. Without Jupiter, the architecture of our planetary family would look very different. Saturn, the sixth planet, is perhaps the most visually striking object in the solar system. Its rings are wide, bright, and complex. They stretch over 280,000 kilometers from edge to edge. Yet they are astonishingly thin. In most places, the rings are only about 10 meters thick. Imagine a sheet of paper spread across a football field. That gives you a sense of proportion. The rings are made almost entirely of water ice. Some pieces are tiny, like grains of sugar. Others are as large as houses. They orbit Saturn in countless individual paths, each one following the rules of gravity with perfect obedience. The rings are not a single solid structure. There are billions of individual particles, each one a tiny moon in its own right. Gaps in the rings, called divisions, are carved by the gravitational influence of Saturn's moons. The Cassini division, the most prominent gap, is about 4,800 kilometers wide. It is visible from Earth through a modest telescope. Saturn also has the lowest density of any planet. It is less dense than water. If you could find a bathtub large enough, Saturn would float. That image, a planet floating in water, captures something surprising about its nature. Despite its enormous size, Saturn is remarkably light for its volume. Its composition is mostly hydrogen and helium, the same elements that make up the Sun. One of Saturn's moons deserves special attention. Enceladus is small, only about 500 kilometers across. but it hides an ocean of liquid water beneath its icy shell. Geysers near its south pole shoot plumes of water vapor and ice particles into space. The Cassini spacecraft flew through those plumes and detected organic molecules and molecular hydrogen. Those ingredients are exactly what scientists look for: water, organic compounds, a chemical energy source, the recipe for habitable environments. Enceladus is small enough to fit inside the borders of a single country, yet it may be one of the best places to search for life beyond Earth. The icy particles from those geysers feed Saturn's E-ring, the outermost and widest of its major rings. So Enceladus is not only interesting for its own sake, it is actively contributing material to the ring system of its parent planet. A tiny moon, reshaping the architecture of a giant. The relationship between Saturn and Enceladus is a reminder that size does not determine importance. Small worlds can have enormous influence. Titan, Saturn's largest moon, is a world unlike any other. It is the only moon in the solar system with a thick atmosphere. That atmosphere is denser than Earth's, made mostly of nitrogen with a haze of organic compounds. If you stood on Titan's surface, you would feel a pressure about 50% greater than sea level on Earth. The sky would appear orange, tinted by complex hydrocarbons suspended in the air. Sunlight on Titan is about 100 times dimmer than on Earth. The landscape would feel like perpetual twilight. Titan has lakes and rivers, not of water, but of liquid methane and ethane. The Cassini mission and the Huygens probe landed on Titan in 2005. They revealed a landscape eerily similar to Earth. Rounded pebbles on the surface, made of water ice rather than stone. River channels carved into the terrain. Shorelines along vast hydrocarbon seas. Ligeia Mare, one of Titan's northern seas, covers an area larger than Lake Superior. Rain falls on Titan. Clouds drift across its sky. Seasons change over the course of Saturn's 29-year orbit. It is a world running on a different chemistry, but with familiar patterns. The methane cycle on Titan mirrors the water cycle on Earth. Evaporation, clouds, rain, rivers, lakes. The same process translated into a colder language. Some scientists speculate that life could exist on Titan, using liquid methane instead of water as a solvent. Such life would be utterly alien to us. Its chemistry would follow different rules. Its metabolism would operate at a pace we can barely imagine. Titan runs an active cycle of liquid, clouds, and rain. That alone makes it one of the most fascinating worlds in our system. It is a laboratory for testing whether familiar processes can emerge under radically unfamiliar conditions. Now we move further outward. Uranus, the seventh planet, was the first to be discovered with a telescope. William Herschel found it in 1781. Before that, every planet known to humanity had been visible to the naked eye since ancient times. Uranus changed that boundary forever. It told us the solar system was larger than we had assumed. It also hinted that more discoveries waited beyond. Uranus is an ice giant. Beneath its pale blue-green clouds lies a thick mantle of water, ammonia, and methane ices. The methane in its upper atmosphere absorbs red light and reflects blue, giving the planet its distinctive colour. But the most unusual feature of Uranus is its tilt. The planet rotates on its side, with an axial tilt of about 98 degrees. Most planets spin roughly upright. Uranus rolls along its orbit like a ball. Scientists believe a massive collision early in its history knocked it over. That collision left a permanent mark on everything about the planet, from its seasons to its magnetic field. Because of this extreme tilt, Uranus has the most dramatic seasons in the solar system. Each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness. Imagine living through a night that lasts 4 decades. When Voyager 2 flew past Uranus in 1986, the planet appeared almost featureless, a pale, quiet sphere. Later observations from the Hubble Space Telescope revealed subtle cloud bands and storms hidden beneath the haze. Uranus is not as calm as it first appeared. It simply keeps its turbulence well concealed. The planet's magnetic field is also peculiar. It is tilted 60 degrees from the rotational axis and does not pass through the center of the planet. Most planetary magnetic fields are roughly aligned with the spin axis. Uranus breaks that rule entirely. The field wobbles as the planet rotates, creating a chaotic magnetosphere unlike any other in the solar system. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Miranda, one of the smaller moons, has a surface so fractured and varied that scientists initially struggled to explain it. Cliffs on Miranda reach heights of 20 kilometers. That is roughly 10 times the depth of the Grand Canyon. Some researchers believe Miranda was shattered by an impact and reassembled under gravity. The pieces came back together in a jumbled arrangement. Others think tidal heating created the unusual terrain. Either way, Miranda is a small world with a dramatic face. Neptune, the 8th and final major planet, orbits far from the Sun. Its average distance is about 4.5 billion kilometers. Sunlight takes over 4 hours to reach it. From Neptune, the Sun would look like a very bright star, not much larger than any other point of light in the sky. Yet, even at that distance, the Sun's gravity still holds Neptune in a steady orbit. The reach of gravity is quietly astonishing. Neptune is a deep, vivid blue. Like Uranus, methane in the atmosphere accounts for the colour. But Neptune is a far more active world. When Voyager 2 arrived in 1989, it found the fastest winds ever recorded on any planet. Speeds exceeded 2,000 kilometers per hour. That is faster than the speed of sound on Earth. The source of that energy is still debated. Neptune receives very little sunlight, yet it radiates more than twice as much energy as it absorbs. Something internal, perhaps residual heat from its formation, drives those ferocious winds. Neptune has a moon named Triton. It is the largest of Neptune's 14 known moons, and it orbits in the wrong direction. Every other large moon in the solar system orbits in the same direction as its planet's rotation. Triton does the opposite. This suggests that Triton was not born alongside Neptune. Instead, it was likely a wandering body from the Kuiper Belt, captured by Neptune's gravity long ago. Triton's surface is one of the coldest in the solar system, around -235 degrees. Yet even there, geysers of nitrogen gas erupt through the surface. Cold does not mean still. Even at the edge of our planetary family, activity persists. Triton's capture must have been a dramatic event. It likely disrupted Neptune's original moon system, scattering or destroying smaller satellites in the process. Neptune also has a faint ring system. Like Jupiter's rings, Neptune's are dark and difficult to observe. They are made of dust and ice particles, organized into several named arcs. The Adam's ring, the outermost, contains bright clumps of material that should have spread out evenly long ago. The gravity of a nearby moon, Galatea, appears to keep these arcs confined. Even in the outer solar system, the dance between moons and rings continues. The ice giants, Uranus and Neptune, remain among the least explored worlds in our solar system. No dedicated mission has visited either since Voyager 2 in the 1980s. Both planets hold mysteries about their interiors, their weather, and their moons. Future missions may reveal entirely new categories of phenomena. For now, they remain two blue sentinels at the edge of the planetary family, waiting for us to return. Beyond Neptune lies a region so vast it dwarfs everything we have discussed so far. The Kuiper Belt extends from about 30 to 50 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. So the Kuiper Belt begins 30 times farther than Earth and stretches outward into deep cold. It is a frozen archive of the solar system's earliest material. This region is home to thousands of icy bodies. Some are small, just a few kilometers across. Others rival dwarf planets in size. Pluto, once considered the 9th planet, lives here. It was reclassified in 2006, not because it shrank, but because we learned the Kuiper Belt held many similar objects. The decision sparked public debate. Many people felt a personal connection to Pluto, but the reclassification was not a demotion. It was a recognition that the solar system is richer than we thought. Pluto did not lose its significance. It gained company. Ceres, discovered in 2005, is actually slightly more massive than Pluto. Makemake and Haumea also orbit in this belt. Each one is a frozen world with its own personality. Pluto has a heart-shaped nitrogen ice plain called Sputnik Planitia. Haumea spins so fast it has elongated into an egg shape, completing a full rotation in under 4 hours. Makemake appears reddish-brown, coated in frozen methane that slowly darkens under cosmic radiation. The New Horizons spacecraft flew past Pluto in 2015. The images it returned stunned the scientific community. Pluto was not the dead, featureless ice ball many had expected. It had towering mountains of water ice and glaciers of nitrogen. A thin, hazy atmosphere wrapped the surface, mostly nitrogen, with traces of methane. The surface showed signs of geological activity far more recent than anyone had predicted. Some regions appeared to be less than 10 million years old. On a body so far from the Sun, something is generating enough heat to reshape the surface. The exact source remains a mystery. Perhaps radioactive decay in the interior provides enough warmth. Perhaps tidal interactions with Charon play a role. Whatever the answer, Pluto defied expectations. It reminded us that distance from the Sun does not mean absence of activity. Even at the edge, geology persists. After Pluto, New Horizons continued deeper into the Kuiper Belt. In 2019, it flew past a small object called Arakoth, formerly known as Ultima Thule. Arakoth looks like a flattened snowman, 2 lobes gently resting together. Its surface is smooth and reddish, covered in organic compounds darkened by radiation. Arakoth is a pristine relic. It has remained virtually unchanged since the solar system formed. Studying it is like opening a time capsule sealed 4.5 billion years ago. The gentle contact between its 2 lobes suggests it formed through a slow, delicate merger. Not a violent collision, but a whisper of a touch. Pluto also has 5 known moons. The largest, Charon, is so big relative to Pluto that they orbit a common centre of gravity. That centre sits between them in open space. They spin around each other like 2 dancers holding hands. From one side of Pluto, Charon never rises. From the other, it never sets. It simply hangs in the sky, motionless, forever in the same spot. Charon itself has a reddish polar cap made of organic compounds processed from Pluto's escaping atmosphere. Material drifts from Pluto to Charon and is transformed by ultraviolet light into a dark, rust-coloured deposit. Think of it as one world painting the other over millions of years. Now picture moving even further out. Beyond the Kuiper Belt, there is a boundary called the heliopause. This is where the solar wind finally weakens. The constant stream of charged particles from the Sun meets the pressure of interstellar space. The 2 forces reach a balance. Voyager 1 crossed this boundary in 2012. Voyager 2 followed in 2018. Both are now travelling through interstellar space, the first human-made objects to do so. They are still sending data back to Earth, though their signals are incredibly faint. Receiving them is like detecting the glow of a single candle from 15 billion kilometers away. Each Voyager carries a golden record, a phonograph disc containing sounds and images of Earth. Greetings in 55 languages, music from Bach to Chuck Berry, the sound of wind, rain, and a human heartbeat. These records were designed as messages to any intelligence that might one day find them. The chances are vanishingly small, but the gesture itself says something about us. We sent our music into the void, just in case. The Voyagers are powered by radioisotope thermoelectric generators, converting the heat of decaying plutonium into electricity. Their power output drops slightly each year. By the mid-2030s, they will no longer have enough energy to operate any instruments. They will fall silent. But they will keep travelling. In 40,000 years, Voyager 1 will pass near a star in the constellation Camelopardalis, about 1.6 light-years away. It will carry our golden record through the dark, long after every human who built it has returned to dust. Beyond the heliopause, the sun's influence fades but does not vanish. Gravity still reaches outward. Far beyond the planets and the Kuiper Belt, there may exist a vast spherical shell of icy bodies. We call it the Oort cloud. No spacecraft has ever visited it. No telescope has directly observed it. But its existence is strongly inferred from the orbits of long-period comets. These comets arrive from every direction, not just from the plane of the solar system. That pattern suggests a spherical source region, like a bubble of frozen debris surrounding the Sun at enormous distance. The inner edge of the Oort cloud may begin around 2,000 astronomical units from the Sun. The outer edge could extend to 100,000 astronomical units. At that distance, the nearest star, Proxima Centauri, is only about 1.3 times farther. The Oort cloud, if it exists as predicted, marks the true boundary of the Sun's gravitational kingdom. It is the outer wall of our solar neighbourhood. The Oort cloud may contain trillions of icy objects. Most are small, perhaps a few kilometres across. They orbit the Sun so slowly and at such great distances that their motion is almost imperceptible. A single orbit at the far edge might take millions of years to complete. These objects are fossils. They have been preserved in deep cold since the birth of the solar system. If we could visit one, we would be looking at material essentially unchanged for 4.5 billion years. A time capsule, frozen at the frontier. Comets born in the Oort cloud sometimes get nudged inward. A passing star's gravity or the tidal pull of the Milky Way can do it. When that happens, they begin a long, slow fall toward the inner solar system. The journey can take millions of years. As a comet approaches the Sun, its surface ice begins to vaporize. Gas and dust stream away, forming a glowing tail that can stretch millions of kilometers. The tail always points away from the sun, pushed by the solar wind and radiation pressure. A comet's tail is not a trail left behind. It is a flag blown outward by the breath of our star. Some comets make the journey only once. They sweep close to the sun and blaze briefly. Then they fly back into the outer dark, never to return within human history. Others settle into shorter orbits. Halley's Comet, perhaps the most famous, returns every 75 to 79 years. It has been recorded by human observers for over 2,000 years. Ancient Chinese astronomers noted it. Medieval European chroniclers feared it. Today we greet it with telescopes and spacecraft. The same icy body witnessed across millennia. That continuity is quietly moving. Comets also carry water. The hydrogen in some comets matches the hydrogen in Earth's oceans. It is possible that comets delivered a portion of our water during the solar system's early bombardment period. Every glass of water you drink may contain molecules from the outer solar system, molecules that once travelled aboard a frozen wanderer. Between all these large objects, the solar system is filled with smaller debris. Meteoroids, dust grains, and microparticles float everywhere. When a meteoroid enters Earth's atmosphere, friction heats it to a glow. We call that streak of light a meteor. Most meteors come from particles no larger than a grain of rice, yet they produce enough light to be seen from 100 kilometers below. If the object survives its passage and lands on the ground, it becomes a meteorite. Some meteorites are older than Earth itself. They carry minerals that formed in the earliest moments of the solar system. Holding one is like holding a fragment of the original cloud, a piece of the beginning resting in your palm. Meteor showers occur when Earth passes through the trail of debris left behind by a comet. The Perseid shower in August comes from Comet Swift-Tuttle. The Leonids in November trace back to Comet Tempel-Tuttle. Each shower has its own parent comet and its own character. Some produce a handful of meteors per hour. Others, in rare outburst years, fill the sky with hundreds. Ancient observers called these events star storms. They were terrifying and beautiful. Today we understand the mechanism, but the beauty remains. The sun has a cycle. Roughly every 11 years, its magnetic field reverses polarity. During the peak of this cycle, sunspots multiply and solar flares erupt. Coronal mass ejections fling billions of tons of charged particles into space. These events can disturb Earth's magnetic field, creating geomagnetic storms. During such storms, the aurora borealis and aurora australis expand to lower latitudes. People in places that normally never see the northern lights suddenly witness green and violet ribbons. They dance across the sky in silence. The aurora is the visible signature of our planet's magnetic shield doing its work. Solar flares also affect technology. Intense flares can disrupt satellite communications, damage power grids, and confuse navigation systems. In 1859, a massive solar storm called the Carrington event caused telegraph lines to spark and catch fire. If a storm of that magnitude struck today, the consequences for our connected world would be significant. The Sun, even from 150 million kilometers away, still has the power to reach into our daily lives. The solar wind, even in calm periods, shapes the entire solar system. It creates the heliosphere, a vast bubble of influence extending far beyond the planets. Inside this bubble, the Sun's particles dominate. Outside, the interstellar medium takes over. That boundary is not static. It breathes, expanding and contracting with the solar cycle. Our entire solar system moves through the galaxy wrapped in this cocoon, like a ship trailing its own wake through the ocean. Gravity is the architect of the solar system, but resonance is its artist. Orbital resonance occurs when two orbiting bodies exert regular gravitational influence on each other. Jupiter and several of its moons demonstrate this beautifully. Io, Europa, and Ganymede are locked in a 4:2:1 resonance. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This pattern has persisted for billions of years. This pattern generates tidal forces inside Io so intense that the Moon is violently active. It is the most volcanically active body in the solar system. Hundreds of volcanoes dot its surface. Lava flows paint the landscape in shades of orange and yellow. All of this heat comes not from a star, but from the rhythmic tug of gravity. Io's interior is kneaded like bread dough by the constant flexing of its shape. Europa, caught in the same resonance, experiences milder tidal heating, but it is enough to maintain a liquid water ocean beneath a shell of ice. That shell is roughly 15 to 25 kilometers thick. The ocean may contain more water than all of Earth's oceans combined. The surface of Europa is crisscrossed with reddish-brown lines. These are fractures in the ice, filled with material that has welled up from below. Some of these features look remarkably like ice rafts that have broken apart and refrozen in new positions. The ice is alive with motion, even if that motion happens over thousands of years. Where there is water, warmth, and chemistry, the possibility of life follows. Europa is among the highest priorities for future exploration. The Europa Clipper mission aims to fly past Europa dozens of times. It will map the surface and measure the thickness of the ice shell. It will search for plumes of water vapor, similar to those on Enceladus. If the ocean contains the right chemistry, Europa could harbor microbial life. Not on the surface, which is bathed in radiation from Jupiter's magnetic field, but deep below, where warm water meets rock. Life on Europa, if it exists, would have emerged independently from life on Earth. That would mean life is not a fluke. It is a tendency. a direction the universe leans toward when conditions allow. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It has its own magnetic field, the only moon known to possess one. Beneath its icy surface, Ganymede likely harbours a layered ocean, sandwiched between ice layers of different densities. Picture a series of water and ice shelves stacked like floors in a building. Each one sits at a different pressure and temperature. Callisto, the outermost of Jupiter's 4 large moons, tells a different story. Its surface is ancient, heavily cratered, and shows no signs of recent geological activity. Callisto may also have a subsurface ocean, but one that is quieter, less active, and perhaps less hospitable. It is a world that time has treated with patience, preserving a record of impacts stretching back billions of years. Callisto's surface is one of the oldest landscapes in the solar system. Every crater is a timestamp. Think of these 4 moons together. Io, burning with volcanic fire. Europa, hiding an ocean of possibility. Ganymede, layered and magnetic. Callisto, scarred and silent. All 4 orbit the same planet. All 4 formed from the same disk of material. Yet each became profoundly different. The solar system is filled with such variation. Neighbours do not mean twins. Now consider something invisible but powerful. The Sun loses mass constantly. Every second, through fusion and the solar wind, it sheds roughly 4 million tons. Over its entire lifetime, about 4.6 billion years, it has lost roughly the mass of Jupiter. That sounds enormous, but compared to the Sun's total mass, it is a tiny fraction. The Sun will continue burning for another 5 billion years before it exhausts its hydrogen fuel. When that fuel runs low, the core will contract and heat up. The outer layers will expand enormously. The Sun will become a red giant. It will swell past Mercury's orbit, perhaps past Venus, and possibly reach where Earth orbits today. The inner solar system will be consumed or transformed beyond recognition. Mars may survive, but only barely. The giant planets will endure, though their atmospheres may change in the new conditions. Their icy moons might briefly warm. For a time, Europa's ocean could be exposed to sunlight. Enceladus might shed its frozen shell. Worlds that were too cold for billions of years could have a brief window of warmth. Eventually, the outer layers will drift away into space, forming a beautiful shell of glowing gas called a planetary nebula. At the centre, the core will remain as a white dwarf, a dense, fading ember no larger than Earth, but carrying nearly the mass of the Sun. It will radiate leftover heat for billions of years, slowly cooling, slowly dimming, until it becomes a black dwarf, a cold, dark remnant. No black dwarf exists yet in the universe. The cosmos is not old enough. It takes longer than the current age of everything for a white dwarf to fully cool. That fact alone tells you how patient the universe truly is. The solar system, then, is not permanent. It had a beginning. It will have an ending. But between those 2 points, trillions of moments unfold. Moons orbit planets. Comets drift in silence. Ice shifts beneath the surface of distant worlds. And somewhere, on one small blue planet, someone lies still in the dark, listening to the story of it all. Every atom in that person was forged somewhere in this system, or in the stars that preceded it. We are not observers of the solar system. We are participants, made from the same materials, bound by the same gravity, warmed by the same star. The spaces between planets are not truly empty. A thin haze of hydrogen atoms, leftover solar wind particles, and interplanetary dust fills the void. Sunlight scatters off this dust, creating a faint glow visible just before dawn or after sunset. We call it the zodiacal light. It is so faint that most people have never noticed it. But from a dark location, far from city lights, it appears as a soft triangular glow rising from the horizon. You are seeing sunlight reflected off particles that have been drifting through the solar system for millions of years. Each planet's magnetosphere tells a story of its interior. Earth's magnetic field is generated by the churning of liquid iron in its outer core. Jupiter's comes from metallic hydrogen. Mercury's is weak but present, suggesting a partially molten core. Venus and Mars have no global magnetic fields today. Venus lost its field for reasons still debated. Mars lost its field roughly 4 billion years ago, and the consequences were severe. Without magnetic shielding, the solar wind eroded its atmosphere molecule by molecule. Mars dried out. Its oceans vanished. Its sky thinned to almost nothing. Magnetic fields are invisible armor. We rarely think about Earth, but it deflects the harshest particles from the sun. Without it, life on the surface would be far more difficult. The magnetic field does not just protect, it also traps particles, creating the Van Allen radiation belts. These belts are regions of high-energy particles looping along magnetic field lines. Spacecraft passing through them must be designed to withstand the radiation. Even something invisible can be hazardous, and even something hazardous can be beautiful. The same particles trapped in these belts eventually spiral down toward the poles. When they collide with atmospheric gases, they create the aurora. Danger and beauty intertwined. The solar system also contains a feature so subtle it is easy to overlook. The plane of the ecliptic is the flat disk in which most planets orbit. It is tilted about 60 degrees relative to the plane of the Milky Way. Our entire system travels through the galaxy at roughly 828,000 kilometers per hour. We complete one full orbit around the galactic center every 230 million years. Dinosaurs roamed the Earth roughly 1 galactic year ago. The solar system is not stationary. It is on its own vast journey, carrying us through a galaxy of 400 billion stars. And most of those stars likely have planets of their own. We have travelled a great distance tonight. From the collapsing cloud where it all began, through the burning heart of the sun, past rocky worlds baked by heat and frozen worlds veiled in ice. We drifted through rings of shimmering particles and past geysers erupting on tiny moons, then into the deep silence beyond the last known planet. We followed comets falling inward and spacecraft sailing outward. We watched volcanoes burn on a moon the size of a small country, and imagined oceans hidden beneath shells of ancient ice. Along the way, we found patterns, gravity shaping orbits with invisible hands, resonance tuning moons into rhythmic harmony, magnetic fields standing guard over entire worlds, and water appearing again and again beneath ice, inside plumes, within ancient riverbeds. Always water, always the quiet suggestion that the universe is more hospitable than it first appears. The solar system is not a collection of separate objects scattered at random. It is a family, born from the same cloud, governed by the same star, connected by the same force that holds your body to the ground beneath you right now. The same gravity that bends a comet's path also keeps the moon in its steady arc across your window. You do not need to remember every detail from tonight. The names, the numbers, the distances. Let them soften. Let them settle into your mind at their own pace, like dust drifting through a beam of light. What matters is the feeling, the sense that you are not separate from any of this. You are made of the same elements forged in ancient stars. The calcium in your bones, the iron in your blood, the oxygen filling your lungs right now. All of it came from the cosmos. Your breath is slowing. Your body is heavy and warm. The pillow beneath your head is solid. The blanket across your shoulders is real. And outside, the same sky we explored tonight is quietly turning above you. Planets are orbiting. Moons are circling. Comets are drifting in silence. And everything is held in place by the same patient gravity that has been working since the very beginning. If you enjoyed this journey, you might like to explore another before sleep fully arrives. And if you feel like it, liking or subscribing helps others find their way here as well. Sleep well and good night.